Okay, hi everyone. Welcome to another Graphs and Matroids seminar. Today we've got our own Jim Geelen from the University of Waterloo, who's going to be talking about, I guess, a Ramsey theorem for Matroids, perhaps. Go ahead, Jim.
Okay, thanks, Shayla. So I'm going to talk about some conjectures I've been thinking about for the last few months now. So the formal title of the talk is this Ramsey's theorem for Matroids? And the informal title is So You Think You've Got Problems? If you don't have enough problems, then I have some to share with you. Don't worry. So I came up with these problems recently, and I have discussed them with a bunch of people, including Rutger Campbell, James Davies, Matthew Croker, Rose McCarthy, Peter Nelson, and Jeff Whittle. And this certainly wouldn't have developed to the sort of state it is now if it wasn't for input from them. So I thank them for their input. So let's jump straight in and look at a special case of the conjectures, or the version for lines. So what we're looking at is we have a simple rank R matroid, and I bound the line length. So I tell you there's no line of length longer than L. And I'm going to two-color the elements, and I want a monochromatic line. And to get a monochromatic line, I'm going to need that the rank is large relative to L. Okay, so that's what I believe is true. So this is reminiscent of Ramsey's theorem in the special case for triangles. If I've got a 6-vertex complete graph and I two-color the edges, then I get a monochromatic triangle. One thing I like about the theorem is the fact that the underlying object that we have isn't a very highly symmetric object like a complete graph or a projective geometry. It's just an arbitrary matroid. One thing that worries me about the conjecture is that it's extremely natural. But I haven't seen it before, so I wonder if maybe it's obviously false. But I haven't been able to think of a counterexample. So I'm sticking with it as a conjecture. Now in this talk, I'm only going to be talking about simple matroids, and I'm going to stop saying simple. So everywhere I say matroid, I mean simple matroid. So here are two special cases of the conjecture that are interesting in their own right. There's a geometric Ramsey theorem for lines. It says that if you take a projective geometry over a field, and the projective geometry has sufficiently large rank, you two-color the points in the projective geometry, you get a monochromatic line. So that's a fairly classical Ramsey theorem. There's a similar theorem for affine geometries. You take an affine geometry and two-color the points, and you're in high enough rank, you'll get a monochromatic line. The version for affine geometries is actually quite powerful. It implies the geometric Ramsey theorem for lines, but actually more than that, you can actually get the general geometric Ramsey theorem from it, where you're looking at not lines, but rank K flats. And it's basically by looking at extension fields down here, you can get this more general version. So the second theorem is actually already a fairly sophisticated theorem, and it's a very special case of the conjecture that I wrote down on the previous slide. So if the result's true, it's probably going to be a little bit tricky to prove. So I just want to mention briefly that this condition here on the line length in the conjecture is necessary. And the reason it's necessary is that if you look at the geometric Hales-Jewett theorem that I just mentioned, the bounds on the rank in that theorem are known to necessarily depend on the field size. So that means in this theorem you're going to have some dependence on the maximum line length. So you can't get away from that. Okay. So for the purpose of this talk, I'm going to take real representable matroids as the starting point. So there are these two beautiful classical theorems about rank 3 real representable matroids. There's the Sylvester-Gallai theorem, which was actually conjectured by Sylvester in about 1890 and proved by Gallai in around 1940. And what he proved was every rank 3 real representable matroid has a 2-point line. Then there's the Motzkin-Rabin theorem that says that in any 2 coloring of the points in a rank 3 real representable matroid, you get a monochromatic line. So that's already very reminiscent of our conjecture. And interestingly, in this context, you don't have any conditions on line length. There is another theorem, I forget the name of the theorem, that says that the average line length in a real representable matroid is less than 3, which sort of proves the first result, but also gives some justification for the second. Okay, so despite the fact that the Sylvester-Gallai theorem was open for 50 years, it's got a really pretty proof. And it's not really relevant to this talk, but since I'm talking about the Sylvester-Gallai theorem, I think I really ought to say the proof in case anyone out there hasn't seen it before. So what you do is you look at the lines in your matroid and the points, and you take a point and a line that doesn't contain it, you take them at minimum distance. So among all points and lines that don't contain that point, you minimize the distance in the plane. And now if I don't have a 2-point line, then that line is going to have length at least 3. And you look at the perpendicular from A to the line, and 2 of the points have to lie on one side. And now you just take this line through these 2 points, and the perpendicular distance to the other point is less than the perpendicular distance from L to A, and you get a contradiction. And that's the proof of the Sylvester-Gallai theorem. It's a very pretty proof. Okay, so I hope there was at least somebody out there who hadn't seen that, because I think it's a really nice proof, and probably more interesting than the rest of the talk. I think the rest of the talk's extremely interesting, but I really love that proof. Okay, so what are we going to talk about? So basically, I'm going to look at to what extent those 2 theorems that's a really bad sentence. To what extent do these 2 theorems extend? I apologize for that sentence. So how far can we push them? So one thing is I would like to, first of all, look within real representable matroids and look at possible generalizations you might make there. And then look at variations for other classes, specifically complex representable and binary. And then we'll finish off by looking at what you can say for matroids in general. So the first observation you can make for these 2 theorems is that while they're stated for rank 3 matroids, they quite obviously hold in any rank at least 3, because you can always just take the truncation to rank 3. If I take a rank 10 matroid, I can just take its truncation to rank 3. That'll still be real representable. I can apply the result there and then lift it back. So if you've proved the result in rank 3, you've proved it in general. And on all of the results that I'm going to look at have that kind of behavior. Once you know them in one rank, you know them in higher ranks. All right, so the Sylvester-Gallai theorem says that if you're in rank 3, you have a 2-point line over the reals. And so the natural question to ask is, if I'm in rank 4 over the reals, do I naturally get a 3-point plane? And the answer is no, and this goes back to Motzkin, I think, in the 1950s. So he came up with several counterexamples. The easiest one is just the direct sum of two triangles. If you take a plane in there, you contain, every plane contains one of the two triangles. So you don't have a 3-point plane. Okay, so that doesn't work. So the geometers think of this as being the right generalization. And that's that every rank 4 real representable matroid has an ordinary plane. And an ordinary plane is a plane that's the union of a line and a point. More generally, an ordinary flat is one that has, when I look at the restriction to that flat, it's the union of a point and a hyperplane. And in fact, Hansen proved that every rank k plus 1 real representable matroid has an ordinary rank k flat. And if you apply that result in the case of k equals 2, it says that every rank 3 real representable matroid has a 2-point line. So I guess it's kind of natural from that point of view, but it does look a little bit weird. Right, you're getting this instead of a 3-point plane. But it turns out that it's extremely useful. If you take an ordinary rank 4 flat, so it's the union of a plane and a point outside, I can then apply the Sylvester-Gallai theorem in the plane to get a 2-point line. And then when I throw in this extra point, that gives me a 3-point plane. So if you have an ordinary rank 4 flat, you automatically get a 3-point plane. And that means that every rank 5 real representable matroid has a 3-point plane. So we kind of hoped it would happen in rank 4, but it didn't work in rank 4, but it works in rank 5, and that's a consequence of this theorem of Hansen. And by the way, this theorem of Hansen's isn't too difficult to prove. His paper's only a few pages long. Okay. And you can just generalize this. You can go in higher rank and you can just sort of repeat. And so you can, with the same technique, you can prove that every rank 2k minus 1 real representable matroid has an independent rank k flat. So that's if you had an independent rank 3 flat, that would be a 3-point plane. And an independent rank 2 flat's a 2-point line. So this is the natural generalization to higher ranks. Geometers refer to these independent rank k flats as elementary rank k flats. And this is best possible because you just take the sum of a bunch of triangles. You can't do better than that. Okay, so that's really nice. That basically is, if you take the Sylvester-Gallai theorem, you get the best, this gives you the best possible answer, like the best bounds that you can have for higher rank independent flats. It also gives you a Ramsey theorem in a trivial and really boring way. So if you take a high rank, and by here high is like 4 times k, you take a high rank matroid, a real representable matroid, and then you 2-color the points, you're going to get a monochromatic rank k flat. How's that? Well, it's going to contain an independent rank k flat of about half its size, half its rank. And then you just take the majority of those. Like some are colored red, some are colored blue, you take the majority. And because it's an independent flat, you get a monochromatic flat. Okay, so because of these flats, because independent flats are sort of relatively boring when you do this, you very easily get the Ramsey theorem. And so this is a sort of a natural extension of the Motzkin-Rabin theorem. So in rank 3, if you two color, you get a monochromatic line, and to get a monochromatic rank K flat, you have to go up to rank about 4K. I don't know what's best possible here. I don't even know if the answer is known. Okay. So let's move to complex representable. It seems very likely that the same kind of phenomenon holds. Maybe we have to go to different rank, but it seems likely in complex representable matroids that if you take a high enough rank complex representable matroid, it's going to contain an independent rank K flat. It's just not possible that I'd be the first person to make this conjecture, but I haven't actually seen it explicitly in print. But there's been a load of work in geometry around these kinds of questions. They don't tend to focus much on really extremal type things. They tend to focus on sort of very concrete questions about rank 3 and 4. The Sylvester-Gallai theorem itself doesn't hold for complex representable matroids. If you just cross out real representable and put complex representable, the ternary affine plane is complex representable, and all the lines have length 3. So that doesn't just give you, that doesn't work exactly. But again, as with the reals, all you have to do is go up 1 in rank and then things become nice. So Kelly proved that every rank 4 complex representable matroid has a 2-point line. And his proof relied on a theorem of, I guess it's Herzenbruch, who works in algebraic geometry, who proved that every rank 3 complex representable matroid has a 2 or 3-point line. So this result is actually apparently quite a tricky theorem to prove, and Kelly's theorem relies on it. So as far as I know, there isn't a theorem about getting a 3-point plane for complex representable. We don't know a bound at all. If you could find an ordinary flat of higher rank, that'd be really useful. Then you could use the same kind of ideas that I mentioned before. But you don't need an ordinary flat. You need something a bit less. So it would be enough if I could find a rank 5 complex representable flat. So if I could, in a rank 5 matroid, in a high rank complex representable matroid, if I could find a rank 5 flat with a point that wasn't in any 3-point lines in that flat, then what you do is you contract that point. You'd be in rank 4, so you'd get a 2-point line. And that 2-point line would lift back to a 3-point plane. You need that there's no 3-point lines, because when you lift back, basically when you contract, you don't want to create parallel elements. So basically, as long as I can find a rank 5 flat with a point that's not in any 3-point lines, then I win. Okay. So if I'm looking for a 3-point plane, it suffices to find a rank 5 flat with a point that's not in a 3-point line in that flat. How might we go about this? Well, I think the first step you might want to try is to bound line length somehow. So if a complex representable matroids, you can have arbitrarily long lines. But if I'm in high rank, presumably I can find a still high rank flat, but lower rank. I can drop down to a lower rank flat, but still with high rank that doesn't contain any really long lines. So maybe I can get down to, say, 3-point lines, similar to the behavior back here. So back here, you could get down to 2 or 3-point lines, and maybe we can do that in general. So maybe if you gave me a high rank flat, I could find a high rank complex representable matroid, I could find a lower rank flat that only has 2 and 3-point lines, or 2, 3, and 4, I don't care, like just some bound. So that would be one step, and I suspect a result of that nature could be proved more or less just by looking in the algebraic geometry literature where the other result came from, but I haven't done that yet. So I suspect that step isn't too hard. And then I suspect that once you've got a bound on line length, there should be a general matroid property that says that if you give me a large rank matroid and you have control on line length, then you should have a rank K flat that only has 2-point lines, or a rank K flat that has no 2-point lines. It's a sort of dichotomy theorem where you get either a flat where all of the lines are 2-point lines or none of the lines are 2-point lines. Right? So you're going from a high rank matroid down to a lower rank flat, cleaning up the lines. I suspect that's true in general for matroids, that you can do that. Again, I don't know how to prove it. But in complex representable matroids, we know there are no rank 4 complex representable matroids whose lines all have length bigger than 2. So this would leave you with no 2-point lines. And if you've got no 2-point lines, then you can do that contraction trick to get a 3-point plane. So if you had these two conjectures here, you would get the result for the complex representable matroids for planes. And I also suspect it's the sort of natural analogues of these conjectures that one could write for looking for higher rank independent flats. But I won't explicitly state those. Okay, so moving on. When we go to binary matroids, things become a bit more weird. So there are binary matroids that don't have 2-point lines in high rank. So in complex representable matroids, that doesn't exist. In rank 4, you already get them. For binary matroids, you get projective geometries and they have no 2-point lines. You also have binary affine geometries that don't have any 3-point line, but have no 3-point planes. The affine geometries have no 3-point lines, but all the planes have 4 points. So again, the affine geometries are what you get from a projective geometry by deleting a hyperplane. Okay. So the behavior is significantly richer in binary matroids relative to this problem of generalizing the Sylvester-Gallai theorem. However, these examples, the projective geometry and the affine geometry, are quite special in some sense. So, for example, a binary matroid with no 2-point plane is a projective geometry. I mean, it's not just that the projective geometry is an example, it's the only example. And what actually got me started in this direction was this theorem that I saw in Kazu Nemoto's thesis that says if you're a triangle-free binary matroid with no 3-point plane, then you're an affine geometry. Now, this is actually a special case of another theorem in the thesis, which is characterizes the binary matroids with no three-point plane. And this special case is actually quite easy because so you've got this triangle-free matroid, so no points in a triangle. And so that means you can use this idea of contracting an element that we were using in the complex case. So whenever I contract an element, I get a matroid with no two-point line. But the binary matroids with no two-point lines are all projective geometries. So I've got this triangle-free matroid, binary matroid, and whenever I contract an element, I get a projective geometry. It's pretty clearly an affine geometry, and there's any number of ways you could prove that. Right, so this is actually a reasonably straightforward consequence of the first observation. Okay. In the context of our discussion here, when we were looking at complex representable matroids, we were conjecturing that if you've got high rank, then you get an independent rank K-flat. And for binary matroids, clearly that's the wrong answer because you do have affine geometries and projective geometries and such. But what's the right question to ask? And I put right in quotes here because what's right for one person isn't necessarily right for another. Like when I read that the right generalization of a two-point line is an ordinary flat in projective geometry, I thought that was a bit weird. So I won't claim to really know what right and wrong mean. But I think a very natural question to ask is, what are the unavoidable flats in high-rank binary matroids? So the unavoidable flats in high-rank complex representable matroids are presumably the independent flats. That's what the conjecture says. What are the unavoidable flats in high-rank binary matroids? What are we forced to see? And the theorem is that if you have a sufficiently high-rank binary matroid, you're forced to see a rank K flat that's either an independent flat, or it's a flat that's isomorphic to a projective geometry, or it's a flat that's isomorphic to an affine geometry. Now, it's not too hard to get started trying to prove this result. So what you do to prove a result of this nature is you fix a basis in your matroid, and then you think of the representation. And I think of the basis as being a set of vertices, and every extra element in the representation as being a hyperedge. And then I just gratuitously throw the Ramsey theorem for hypergraphs at this. And then I can assume that for every size of hyperedge, you either have them all or none. And so you have a very, very special kind of binary matroid. And then you look a little bit for affine geometries and projective geometries in there. And if you don't find a projective geometry or an affine geometry in there, essentially it's not too hard to find an ordinary flat in there. We don't use exactly an ordinary flat, but essentially we find an ordinary flat. And once you have an ordinary flat, you use induction and you do it all again. So this uses basically iterative applications of gratuitous hypergraph Ramsey theorem. So it's presumably the numbers are not so pretty, but I'm sure that we're just being a bit brutal, and the real numbers are probably not too bad. Anyway, that's how we prove that result. And this theorem implies the Ramsey theorem for binary matroids. Right, if I take a two-coloring of the points in a rank R binary matroid, I'm going to get a monochromatic rank K flat. Why is that? It's true because so I first of all find the unavoidable flats. So I find huge rank flats that look like one of these things, and then I apply the Ramsey theorem inside the associated object. In this case here, I only have to do majority. If I get an independent flat, I just color it and then take the majority. But for the projective geometry and the affine geometry, I have to apply certain geometric Ramsey theorems. But we have those geometric Ramsey theorems. So the Ramsey theorem for binary matroids is just an application of this unavoidable flat theorem. Okay. There's another nice corollary of this theorem, and that is that it comes from the observation that projective geometries and affine geometries are basically full of four-element circuits. So if you exclude four-element circuits, if you take a matroid with no four-element circuits, you're forced to get an independent flat. So if you take a large rank binary matroid with no four-element circuits, then it has an independent rank K flat. So this looks a lot like the sort of results we saw over the reals. These generalizations of the Sylvester-Gallai theorem. The only thing is we had to throw in this condition on girth. And I think that that result is probably true in general for matroids. So you can just cross out binary there. And I think this would be really nice if it was true. It's let me go back to this and explain this in the context of looking for independent flats. Projective geometries are obstructions to finding independent flats of rank, so ordinary flats of rank 2. Well, sorry, independent flats of rank 2. The binary affine geometries are obstructions to finding independent flats of rank 3, so 3-point planes. And if I'm looking for independent flats of higher rank, I either get them or I find the obstructions for 2-point lines or 3-point planes. And it sort of says that there's no obstructions for other flats above that. So it's not like there's a hierarchy of obstructions. You have obstructions for 2 and 3, and then that's that. And then the obstructions for 2 and 3 are also obstructions for everything higher. And this conjecture is saying that that sort of behavior is true for matroids in general. So I really like that conjecture. So this is describing what's going on for matroids with girth at least 5, but now what about general matroids? Can we say something about the unavoidable flats in general? I don't have a really strong explanation for this, but I don't think there's going to be a really nice answer in full generality. So you give me an arbitrary matroid, I can say the unavoidable high rank flats look like these. And basically it's because I can construct some things that are relatively complicated. So you can do things like, if you've got a field with nested subfields, you can take a projective geometry over one of the subfields, and then you can put on top of it an affine geometry from a different subfield and an affine geometry on top of that from a different subfield. And if you can do this in certain ways, I think they have to be nested when you're doing it, that end up with sort of bizarre behaviors. If you fix the field that all goes away because you can't take, I mean, there's a fixed number of nested subfields, and so you can just take the rank to be large enough to get rid of issues like that. But if you don't fix the field, so if you're not bounding line length, you can get fairly complex behavior. But this looks a bit arbitrary. So why fix line length? Do you also need to bound the number of points in planes? You can make matroids, so I could start out with a binary projective geometry, so the line lengths are all 3, and then I can go into one of the Fanos sitting in that projective geometry, and I could principally truncate it. Well, maybe that's a bad example. I could go to a rank 4 binary projective geometry and principally truncate it, and then I get a very dense plane there. So I can get flats floating around that are really dense, even though the line length's only 3. So I can make very dense planes by principal truncation, or basically any kinds of projection. So you can get really dense planes, but can you do it a lot? And I can't think of a way one could do it a lot. So I actually conjecture that if you bound the line length, then you can also bound the number of points if you go down to a smaller rank. So if I take a huge rank matroid with bounded line length, then I can go down to a rank k flat with at most L to the k points. And I think something stronger is true. Not only is this flat got at most L to the k points, but if I take a rank t flat in it, it's got at most L to the t points. So that its subflats will also be nice. So in some sense, you should be able to clean up all of the other flats once you've cleaned up lines. So once you've bound line length, that should lead to control over the density of other flats in your matroid. I'd love to see a proof of this. And in fact, I don't care about this particular function. This function here is just defined because I know that you can get that many in affine geometries. Okay, so you're not going to be able to do better than that, but any function here, like bounding the number of points as a function of L and K is what I really care about. It's kind of hard to imagine that you can do much in the way of Ramsey theory if you're not controlling the number of points in low rank flats. If all of your planes had a load of points, how are you supposed to apply Ramsey theory? Okay, so here's a first guess at a conjecture for the unavoidable flats in a matroid when you bound line length. So obviously one thing you could end up with is large independent flats. These are great. We love those. And then the conjecture is saying that what we saw in the case of binary matroids, the same kind of thing could happen. So you might have a high rank flat that doesn't have any 2-point lines. All the lines have length at least 3. Or you might have a high rank flat where every line has 2 points, but you don't have any 3-point planes. Right? The affine geometries had this property. All of the lines had 2 points, but you had no 3-point plane. And the projective geometries had this property that all of the lines had 3 points. So sort of the first stab at things is that you have this kind of property. And again, this is saying that your obstructions to large independent flats, you have some interesting ones for 2 and 3, but you don't have things above that. And then you might want to further refine these things. So say I gave you a huge rank matroid there, and I tell you that all the lines are only 2-point lines, but it doesn't have any 3-point plane. So that's saying that you have a load of 4 circuits. There's no 2-point, there's all the lines are 2 points. So if you take any 3 points, they're going to span a 4th point. So every triple is in a 4-element circuit. What is your matroid? Well, it can still be pretty complicated, because you could do something, for example, you could take certain projections of affine geometries, principal truncation and such, binary affine geometries. So there's some reasonably complicated things you can do in here, but maybe they all contain big binary affine geometries. I think actually that's reasonably likely. I'm reasonably convinced that that is the outcome. So it's quite hard to line up a whole bunch of 4-element circuits nicely in a matroid. And we have to be doing this all over the place. It's hard to do that without constructing an affine geometry. So I think that this second outcome, again, I'll be slogging the rank here. So I'm not necessarily saying that the matroid I'm looking at was an affine geometry, because that's just not true. But I can, because I'm dropping the rank, I can just drop the rank a bit further, and I can make that R a bit larger to begin with and end up with an affine geometry in this case. Okay, so what about this other outcome? So the first outcome is fantastic. You've got an independent flat. This outcome is now fantastic because it's just a specific matroid. But here, every line, so I'm looking at matroids, large rank matroids, where every line has at least 3 points, but I also have a bound on the line length, right? I mean, it's not just arbitrary line lengths. I've got some bound on the line length, but I'm telling you that all the lines will have length at least 3. What might you expect to have in this case here? Well, it seems pretty natural. If I've got an upper bound and a lower bound on the line length, and the line length can be huge, it seems pretty natural that you might find some flat in there where all the lines have the same length. You might be able to sort of iteratively say, I get all lines of length at least 4, or all lines of length at most 3, and then just keep repeating things like that. This looks like a plausible conjecture to me. And here's a weird question. Are there matroids of large rank whose lines all have length exactly 15? 15 is specially chosen because 15's not a prime power and 14's not a prime power. So projective geometries, the line length is q plus 1, and affine geometries, the line length is q. So if you have a number that's a prime power or a prime power plus 1, then you can construct matroids of arbitrarily high rank having that line length everywhere. But I don't know of a matroid, I don't know how to construct a matroid with large rank whose lines all have length exactly 15. And I would guess you can't. So I kind of feel that high rank matroids where all the lines have exactly the same length probably contain affine or projective geometries. I'm not very confident in this conjecture. I'll call this the wild version because this is definitely, I think, slightly dubious. But The other conjecture I was more happy with. This I find a bit more of a worry, but maybe the following is true. So maybe the unavoidable flats are just independent sets, projective or affine geometries, exactly the same as we saw for binary matroids, but these projective and affine geometries could be over any field. Well, not any field because the line length's bounded, so it has to be one of the fields that are covered by the line length bound. But maybe those are the unavoidable flats. If those were the unavoidable flats, then you would get the conjecture theorem for the Ramsey's theorem for matroids. That conjecture would follow because you first of all pull out your unavoidable flat and then you apply the associated Ramsey theorem inside the nice flat you get. Okay, so I think this conjecture is incredibly interesting. I like that conjecture a lot too. It's probably a lot more natural looking than that conjecture, but I think this conjecture would be really saying a lot about structure of what's going on inside matroids. It's, I think, quite an appealing conjecture. Okay, so let me just finish off by summarizing some of the things we do and don't know at this stage. So we've got this Ramsey theorem for matroids. As I explained in the talk, it holds for real representable matroids for fairly straightforward reasons, and for binary matroids also for fairly straightforward reasons. We know a little bit more about the case for lines. We know that the result holds for lines in the case that the line length is 3. So if your lines have length 2 or 3, and you two color the, so I take a simple rank R matroid whose lines all have length 2 or 3. If R is large enough, and you two color the elements, then you get a monochromatic line. We know that's true. And that's true for a strange reason. So if you want to prove this conjecture, you can make the following observation. So when I truncate this matroid down to rank 3, if I had this really high rank matroid and I truncate it down to rank 3, I get a rank 3 matroid with a lot of points, but still the line length is the same. Right? When I truncate down to rank 3, the lines stay the same. So I keep the same structure of lines, and I just end up with a lot of points. And so you could ask yourself, does the same conjecture hold if I just ask that you have a lot of points and I'm in rank 3? So I do a lot of points in rank 3 with bounded line length, force a monochromatic line in a 2 coloring. And for line length, for lines of length 2 or 3, that's true. And it's quite easy to prove. So this is a pretty easy exercise in this case, but it's false for when you have lines of length 4. So Rose came up with an example where all of the lines have length 4, and you have a 2 coloring which doesn't work. So that's the state of what we know. We have this theorem for real representable matroids, binary matroids, and we have this lines conjecture when the line length is 3. And at this stage, that's all we know. And that's where I'll leave it. Thanks for your attention.
Great. Thank you so much, Jim. Lots of great conjectures there. Everyone, let's unmute and we'll do a round of applause. So I'll count to 3 and then we'll clap. 1, 2, 3. Excellent. And does anyone have any questions for Jim? You can just go ahead, unmute and ask your question.
You said that the ranks that you're dealing with are going to be pretty large. Do you have any estimate for them?
I don't know that they're going to be large. It's just the proofs that I gave were bad. I mean, in the complex case, for example, I think that, the numbers are probably really nice, like they are in the real case. And I don't suspect they're much worse in the complex case. I mean, you can get slightly, like, it's not going to be like +1 in that case. It might be like a multiple of 3 instead of 2 or something like that, because of the low rank counterexamples push up, because you can take direct sums of lower rank counterexamples to get higher rank things. So for example, I've got this rank 3 matroid that doesn't have 2-point line. So if I take the direct sum of that thing twice, I get a rank 6 matroid that doesn't have 4-point independent flat. So you can do tricks like that. You can, so the way it grows is going to be related to the counterexamples you've got, but presumably those things are about the right numbers.
Okay. Thanks.
And then for binary matrices, I have no clue. I mean, we just threw Ramsey theory at it and just sort of took the theorem. We didn't do any. I mean, it might be that there's some really good bounds there. I have no idea.
Thanks. Nice talk. I've got to go and teach, so I'll have to leave. Sorry. Cheers.
Okay, see you, James.
Does anyone have any other questions? Maybe I was going to ask, like, for proving some of those conjectures, do you think it's worth it to try looking at other classes of matroids first? And if so, which classes do you think you'd be interested in?
Well, Matt and I are thinking about other finite fields. And a lot of this machinery just works, but then we haven't cleaned up the last step where you have to do the iterative thing. But some of the conjectures might be, I would guess that the complex representable case, one could probably look at some of those papers and just see what they applied and probably get some interesting results. I'm not sure if you would get the whole result directly, but I'm pretty sure that you'd get something interesting if you spend a bit of time looking at the complex case.
Okay. Last chance for questions on the recording. All right, I'm going to stop the recording. We can have some more discussion.